Hello everyone, welcome to our presentation. Today we are going to talk about security analysis of Ripple consensus. This is a joint work from researchers from cryptology and data security group from University of Bern. My name is Jovana Micic and my co-authors are Ignacio Amores-Sesar and Professor Cachin. So let's start from giving a short introduction of Ripple basics. So Ripple is a blockchain-based platform that enables secure and instant worldwide transactions at low cost, and it has native cryptocurrency XRP. Unlike Nakamoto's consensus protocol in Bitcoin or Ethereum, the Ripple consensus protocol does not rely on mining. Instead, it uses a voting process relying on the identities of its validator nodes to reach consensus. This makes Ripple much more efficient than Bitcoin for processing transactions, which is up to 1,500 transactions per second, and it lets achieve very low transaction settlement times, which is between 4 to 5 seconds, which is quite fast. Now let's take a bit more from technical perspective into the Ripple protocol. So protocol itself is generally considered to be a Byzantine fault-tolerant agreement protocol, which can reach consensus in the presence of faulty or malicious nodes. In contrast to traditional Byzantine agreement protocols, there is no global knowledge of all participating nodes, but each node declares a unique node list, shortly called UNL, of other nodes that it trusts. In the next slide, I'm going to show you an example how this actually looks like and how it's configured. So the peer-to-peer network consists of many independent Ripple servers that receive and process transactions. In our talk, we will always refer to the nodes that take part into consensus, and they are called validating nodes. And here I want to show you now an example where we have 6 nodes in the Ripple network, and first 4 nodes are in UNL 1 and last 4 nodes are in UNL 2. Nodes 1, 2 and 3 trust to UNL 1 and nodes 4, 5 and 6 trust to UNL 2. The overlap between UNLs, two UNLs is 50%, and maybe it's good to explain what does it mean that node trusts to some UNL. It means that, for example, node 1 will listen only to messages coming from nodes 2, 3 and 4. And based on these messages, node 1 will make its own decision or give a vote for some transaction. In order to reach a consensus among the all nodes, there must be an overlap between each UNL, as I already said, and most of previous work was trying actually to discover what is the minimum required overlap, and you can find more in the previous papers regarding the Ripple about this. And what Ripple company guarantees is that the protocol will work if your node that you are configuring has 100% overlap with the list of validators which is recommended by Ripple. And this is how we configure the node. So basically we have 2 files, Ripple configuration file and validators txt file. And these files look like this. So here in the picture you can see both files, and they are took from a Ripple Git page, Git project, and these are actually configuration files which are recommended by Ripple to be used. So Ripple configuration file has configured some things like server addresses, ports, database things, and many other things. But for us, the most interesting here is the part that is highlighted in blue. It points to the file which validators txt, which specify the list of other nodes that our node should trust. And on the right side, we see this file. So basically what is important here is that this file is configured in a way that this node trusts to the list of recommended validators, which are recommended by Ripple. And this is a screenshot of Ripple website where you can see the full list of validators that are recommended. There are 40 recommended validators, and 6 of them are actually from the Ripple Labs, the company that is behind the protocol. But what I would like to mention is that at the beginning, the Ripple validators were mostly coming from Ripple company itself. But now this is changing. There are more validators coming from other institutions or companies, but still we can argue about the thing that if Ripple is really decentralized. And now let's move to more technical part about Ripple Consensus Protocol, and let's see how it actually works. I would like to start first from mentioning that there is not a lot of research have done regarding the topic of Ripple Consensus Protocol, and the previous work has one description of pseudocode, which is not really clear, really hard to understand, and it misses a lot of details. So the main contribution of our work is that we went into the source code, and step by step we have done reverse engineering and created a pseudocode which is 4 pages long, and it contains a high overview of how protocol works, and it contains the most important parameters to understand how the protocol actually works. From these pictures, you don't have to be able to read it or to understand. This is just to show you how big is this. And in general, the whole project is huge with a lot of files. But if you like to know more details and more technical information, you can read all of this in our paper. So let's start from some basics. So we start from a ledger, which roughly plays the role of blocks in other blockchain protocols. A ledger is stored persistently. It consists of a sequence number, then of a batch of transactions, a hash of logically preceding ledger, and it has own ledger hash. Each node locally maintains 3 different ledgers. First is a current ledger, which is in the process of building during a consensus round. Then the previous ledger, which represents the most recently closed ledger, and the valid ledger, which is the last fully validated ledger in the network. The protocol is highly synchronous, although there are parts during validation phase when it's actually asynchronous, but most of the time the protocol is synchronous. It relies on a common notion of time, and it's structured into the successive rounds of consensus, where in each round the protocol agrees on a ledger. And the whole protocol is driven by a heartbeat timer which ticks every second. The protocol rounds and their phases are implemented by a state machine which is invoked every second when the global heartbeat timer ticks. And there are three phases through which consensus goes on during one round. Usual phase transition goes from open to establish and then to accepted phase, and then proceed to the next consensus round, which starts again from the open phase. But it's also possible that the phase changes from established to open if a node detects that it has been forked from others to a wrong ledger. Here is a general overview of how one consensus round looks like, and now we will go through step by step through phases. So let's start from the open phase. So when the node enters a new round of consensus, it sets the phase to open, it resets round-specific data structures, and it waits for the buffer to fill up with submitted transactions. Once the node has been in the open phase for more than half of the duration of the previous consensus round, the node moves to the established phase. During the established phase, the nodes exchange their proposals for the transactions to decide in this consensus round using proposal messages, as you can see in the picture. These proposals may contain different transaction sets, and all transactions on which the proposals from other nodes differ became disputed, so every node keeps the track of how many other nodes in the UNL have proposed a disputed transaction and represents this information as votes by the other nodes. The node may remove a disputed transaction from its own proposal or add one to its proposal, and this decision is based on the votes of other nodes from its UNL. What is interesting is that the node increases the necessary threshold of votes for changing its own vote on a disputed transaction, depending on the duration of the established phase with respect to the time taken by the previous consensus round. So as we can see on this graphic, the far we go into consensus time, the higher is the threshold. And the moment when the node moves to the accepted phase, it is when it has found that there is a consensus on its proposal, and in order to move to the next phase, the node needs 80% of votes of other nodes to match with the proposal that it proposed. Now we move to accepted phase. The node constructs the next ledger or the last closed ledger by applying decided transactions. This ledger is signed and broadcasted to other nodes in a validation message, as we can see in this graphic. After that, node immediately initializes a new consensus round, and concurrently, as I already mentioned, the nodes receive validation messages from the nodes in its UNL, and it verifies them and counts how many other nodes in UNL have issued the same validation. When this number reaches 80% of the nodes in its UNL, the ledger becomes fully validated and the node executes the transaction contained in it. Now Ignacio will talk more about possible violation of safety and liveness.
As Jovana just said, now we introduce the attack that leads to the violation of safety for the Ripple protocol. We studied this attack in a setup with a small number of honest nodes, So in particular we have 7 nodes, one of them is Byzantine, divided in 2 different groups. Nodes 1, 2 and 3, colored in black, they have as UNL nodes 1 to 5, while blue nodes 5, 6 and 7, they have as UNL nodes 3 to 7. Node 4 is the Byzantine node. This node will behave like an honest node until the precise moment to attack arrives. And this moment is exactly when the black nodes, they propose transaction Tx at the same time that the blue nodes, they propose transaction Tx prime. So we trigger the adversary, and the adversary will behave like proposing transaction Tx while interacting with nodes 1 to 3. And he will behave like proposing transaction Tx prime while interacting with the blue nodes 5, 6 and 7. So to study this attack, we focus in the local view of the honest nodes, one in each group, because from the symmetry that we can see in this problem, the node 1 will follow the same steps as node 2 and 3, while node 5 will follow again the same steps as nodes 6 and 7. So we focus in the local view of nodes 1 and 5. These nodes, they only listen to the nodes that they have in their own UNL, so node 1 will only listen to nodes 2, 3, 4 and 5. These nodes, they will send their vote to node 1, and after collecting all the votes, we can see that we have 3 votes in favor of transaction Tx and 1 vote in favor of transaction Tx prime. But remember that we have to consider our own vote. So this means that we have 4 votes for transaction Tx out of 5. This is the 80% that Jovana explained before. So we think that transaction Tx should be added to the new ledger, while transaction Tx prime shouldn't be, because we only have 20% support. However, at the same time, from the point of view of node 5, exactly the opposite happens. We have enough support for transaction Tx prime, while we don't have for transaction Tx. So this produces that these 2 nodes, they will create a new ledger to be validated that they are conflicting, since Tx is only in ledger L and Tx prime is only in ledger L prime. But we go to the second round of consensus when we try to validate these ledgers. And as we mentioned before, the nodes in black, they follow the same steps, and the same happens to the nodes in blue. So when we are in this round, from the point of view of node 1, we receive 3 votes in favor of transaction Tx, in other words ledger L, and 1 single vote against with ledger L prime. And the opposite happens for node 5. As we recall from before, we need 80% of support to approve, to validate this ledger. And we have exactly 80%, because for the case of ledger L, we have the votes in favor of node 2, 3, 1 and the Byzantine node out of 5. So these 2 honest nodes, they will produce different valid ledgers, and they will validate those ledgers, leading to a break of safety. In other words, we have serious problems in the Ripple protocol. But the problem is that our adversary is so greedy. So he's always trying to find better ways to attack. So what she did, she just realized that she can generalize this attack, so we don't need to look for such a precise moment to start the attack. And this is the thing that we introduce exactly right now. In this case, we have again a symmetry problem, because it's easier to study and is the optimal way to attack. So we have some group of nodes that have 1 UNL, these are the nodes in black as before, while the nodes in blue, they have the blue UNL. And it happens as before. We have F faulty nodes, could be F equal to 1, F equal to 700, that they wait for the precise moment to attack, again, breaking safety. Instead of going step by step, trust me, it's the same as we introduced before, and we can derive the following condition of the number of faulty nodes. We need to be greater or equal than 2n, this is the number of honest nodes, and this fraction that depends on omega, which is the overlapping of the 2 different UNLs that we consider. One interesting case is that when the overlapping approaches to 1, we need that f is greater than more or less n. So this translates in approximately the traditional bound that we have for consensus, saying that if the number of malicious nodes are strictly smaller than 1/3 of the total number of nodes, we are safe. But this goes even beyond that, and it's like in the Ripple protocol we can also attack liveness. We saw before that the optimal case for safety is having a huge overlap. However, if we consider a scenario with 2n honest nodes and one single Byzantine node, that they all share the same UNL, we can break liveness. And to do this, we just need to wait until half of the nodes they propose one transaction, while the other half of the nodes they propose a different transaction. In this moment is exactly when we start the attack. The malicious node will behave as proposing transaction TX to the nodes that propose transaction TX, and will behave as proposing transaction TX prime to nodes proposing transaction TX prime. And with this attack, we manage to break the liveness of the protocol, because from the point of view of any of the nodes, we see that what we are proposing strictly has more than 50% of the support in our UNL, which is all the nodes. So we don't change our mind, we keep proposing this transaction, and we don't accept the other one because it has less than 50% support. So we will repeat over and over again, breaking liveness.
And now we are slowly coming to the end of our presentation, and let's sum up some thoughts from our work. So previous work regarding the Ripple consensus protocol has already brought up some concerns about its liveness and safety. So in order to better analyze the protocol, this work has presented an independent abstract description of Ripple consensus method, which is derived directly from the implementation. Furthermore, this work has identified relatively simple cases in which the protocol may violate safety and liveness, and which has devastating effects on the health of the network. And our analysis illustrates that need for very close synchronization and tight interconnection between the participating validators in the Ripple network. That would be all from us. Thank you very much for listening to this talk. And if you're interested in reading more details, the paper is available on request. Thank you one more time.